session. We're delighted to have Jonathan Rosenberg, who will tell us about twisted derived equivalences and string theory dualities with B-field.
Okay, thank you very much. Really appreciate the opportunity to speak here, especially since most of the conference is about stuff that's not really my main specialty, but the conference is supposed to be about kind of connections between mathematical physics and algebraic geometry, and I think you'll see a little bit of that, although the algebraic geometry that will come in will turn out to be of a kind of unpredicted sort. So, but let me start with the connection with physics is admittedly a little bit tenuous, but let me start with that at the beginning so you can see how I arrived at this particular subject. So let's start with type 2 string theory. So then this is a superstring theory in which you have strings moving in a space-time manifold of dimension 10, and it's usually taken to be of this type. So there's a flat Euclidean space, and there's some other compact Kähler manifold, usually with a Ricci flat metric, but we're not going to use the metric at all. Let's say a complex dimension n and trivial canonical bundle. So for me, when I say Calabi-Yau, I'll mean trivial canonical bundle. I'm not necessarily assuming that the manifold is simply connected. And also, I'm just going to stick to the case where M is a smooth projective variety over C. And so then X, the space-time, is a quasi-projective variety, you know, the affine space cross M, all right? So in this situation, the physics, turns out, this is about the only thing you need to know about physics for purposes of this talk, is that the physics is largely controlled by certain submanifolds of space-time, which are called D-branes. So the D isn't a mathematical symbol, it's just an abbreviation for the word Dirichlet, because it comes from Dirichlet boundary conditions for the branes. And so these D-branes are certain submanifolds of space-time, and in type 2b, they're complex submanifolds, and so they have even real dimension. And in type 2a, they have odd real dimension. They're isotropic submanifolds for the symplectic structure. So, I mean, you've heard quite a bit about the symplectic side of things in other talks. Here, I'm mostly going to stick to the holomorphic, or really complex algebraic side of things, which has to do with type 2b. Okay, so now when I said these D-branes are submanifolds, that's a bit of a simplification. Really, you should think of type 2 D-branes as corresponding to coherent sheaves for the algebraic structure, and the type 2a D-branes are classified by things in this mysterious Fukaya category, which I know nothing about, so I'm not going to talk about that. So in type 2b, there's interest. I'm not sure how much interest among real physicists, but the sort of quasi-physicists who are physicists, they're algebraic geometers masquerading as physicists. They're interested in the bounded derived category of coherent sheaves. So that's what I'm going to talk about here. So why the derived category, and why? I mean, so this is constructed out of equivalence classes of complexes of coherent sheaves, not single sheaves. So why do you have complexes? Well, that's because complexes correspond to collections of D-branes that can join together, separate, collapse, etc. And all of those physical processes are sort of encoded in this this derived category over here. So so knowing about the derived category of coherent sheaves tells you quite a bit about the physics, at least from from a kind of theoretical point of view. How you actually translate that into physical calculations that a physicist would care about, I have no idea. That's a job for the physicists. That's not really so much a job for the mathematicians. But while we're on the subject of classification of D-branes, there's a topological classification that's a little coarser than the classification by derived categories. And this was first proposed by Manasian and Moore and Witten. And in this version of things, the D-branes give classes in complex K-theory in even degree. I mean, it has Bott periodicity, so it's periodic of degree 2, in type 2b, and the odd complex K-theory in type 2a. Okay, so for purposes of this talk, I'm going to be talking about the derived category of coherent sheaves and also about these K groups. Now, there are certain variants of string theory which are a little more complicated than that. So I'm going to be talking about what are called Orientifold string theories. So in the sort of basic string theories, you have the space-time manifold X, and you're supposed to think of little strings as moving around in X. So a string is a one-dimensional object, as the name suggests. It's a one manifold, in other words, either a circle or an interval. And a string moving in time gives you a map from a two manifold, in other words, a surface, a real surface, or from the complex holomorphic point of view, it would be a curve, into X. And the theory of these maps is called the sigma model. So the sigma model consists of the maps from sigma into X, and then there are certain differential equations satisfied by this map, and that sort of tells you what the configurations of the strings are. Okay, so in an Orientifold theory, the sigma is equipped with something called the world sheet parity operator, which reverses orientation on the sigma. And you have an involution X, involution on X, which we'll call iota, and you want these strings to be equivariant for those two involutions. So in other words, when you reverse parity on sigma, that corresponds to applying iota on the target. So then when you have X together with the involution, then you get a slight variation in the K theory. It's no longer the K theory of just a space by itself, but it's a space with an involution. Okay, so in the special case where the involution is just the identity map, so then you get what's called the type 1 string theory, which is the string theory where you forget the orientation on the strings. And in general, in the Orientifold theory, the D-brane charges live in KR theory of X together with the involution, which is the so-called real K theory, real with a capital R, real K theory of Atiyah, which was introduced in his famous paper, K theory and reality, reality with a capital R. And in the case where iota is the identity, whoops, sorry. So that's this case over here, that just gives you real K theory instead of complex K theory. Okay, so in the Orientifold theory, if you have trivial involution, this string charge, the D-brane charges live in KO of X. Okay, now a number of years ago, joint work with Chuck Duran and Stefan Mendez-Diaz, we classified the Orientifold string theories that are associated to holomorphic or anti-holomorphic on involutions on elliptic curves. And let me show you a diagram of these theories because it's a little bit complicated. It turns out there are 10 of them, and they're grouped into 3 duality classes. So within each class, the K groups that you get are all the same, except possibly for a degree shift. And And the theories are dual in a certain sense, which is made specific in physics. So let me just exit this for a second and bring up the other picture here. So this was our paper. And here, let me just scroll forward to a picture. There's a place where you have a picture of these things. Oh, here it is. Yeah, here's the diagram. Okay, let me blow this up. Okay, so here's the table of the 10 Orientifold string theories on an elliptic curve. And you see they're color coded. So the ones in yellow all belong to the same class, and you see the K groups that you get are just the real K theory of the two torus. The ones in orange are all in the same theory, all same duality class, and here you get KO plus complex K theory. And for the other duality class that has 4 things in it, you get a copy of two copies of self-conjugate K theory, one with a degree shift. Okay, so see those blue things. So for purposes of this talk, I'm going to be interested in these 2 theories down here. Notice here, there's not even any degree shift. The K groups are exactly the same. So what do those come from? These are theories that are associated to an anti-holomorphic involution. In one case, there are no fixed points. The set of fixed points is empty. That's this case over here. And in the other case, there are 2 components of fixed points. So you have two fixed circles, but one is assigned a plus charge and the other is assigned a minus charge. That charge is called the O-plane charge. And basically what it means is that on each one of these D-branes, you have something called a Chan-Paton bundle, which is a vector bundle. So in the type 2 theory, that's usually a complex vector bundle. But if you have a submanifold which is fixed under the involution, then that involution, since it's anti-holomorphic, gives you an anti-holomorphic identification of this vector bundle with itself. So that ends up putting either an orthogonal or a symplectic structure on the vector bundle. And so there are 2 types of so-called O-planes. O stands for Orientifold, that you can have. They're not really planes, they're submanifolds. But so you can have an O-plane with a plus charge that corresponds to an orthogonal structure on the bundle, or you can have an O-plane with a minus charge, which is a symplectic structure. So notice here we have one of each. In the other cases, the O-planes all have the same charge. Well, here are some cases where you have different charges also. Okay, so all right, so keep that in mind. And now we'll go back to what we were doing before. Okay, so as I said, the most interesting duality group is the one that involves 2 cases with anti-holomorphic involutions. One of them has no fixed points and one has 2 fixed circles but opposite O-plane charge. All right, and the opposite O-plane charge corresponds to a kind of twisted version of KR theory. So these twists in the the twists in the K-theory come from, depending on your point of view, you might say they come from the non-triviality of something which the physicists call the B field, or else they come from some other kind of twisting, which is the sort of twisting that shows up in Karoubi and Donovan's theory of twisted K-theory. Okay, so that's what this thing is. All right. Now, here's the connection with algebraic geometry, which is a little unexpected because, as far as I know, virtually all of the literature on string theory and algebraic geometry deals with complex algebraic geometry, but now real algebraic geometry comes in for the following reason. If you have an anti-holomorphic involution on an elliptic curve, that means that your curve, which is a curve defined over C, is actually really defined over R. And you should think of the anti-holomorphic involution as being the action of the Galois group of C over R. So what you have really is a smooth genus 1 curve defined over R, which may not have any real points. The case where the fixed set is empty, fixed set or things fixed under the Galois group means being empty means that there are no real points in this algebraic variety defined over R. And Karoubi and Weibel, in a very interesting paper in 2003, showed that KR theory of, well, in general, any smooth complex variety with involution is very closely related to the algebraic K theory of the real variety. In fact, with finite coefficients, they coincide. So that suggests that maybe, if we're algebraic geometers, we should be thinking about real algebraic geometry, and we should look at the algebraic K theory of this variety or scheme defined over R. Okay, so that's going to motivate what I'm going to do later. And so therefore, that suggests that maybe the duality of the Orientifold string theories is reflected in an equivalence of derived categories for curves defined over R, where you have to have a twist. Yeah. Well, fundamental domain is artificial. The structure of the real variety is sort of canonically defined when you have an elliptic curve with an anti-holomorphic involution on it. I'm trying to do things in a kind of setting where I don't have to make any artificial choices, because that will give us the sort of most natural setting for the mathematics in some sense. Yeah. Okay. So we'll get to this. That is, in fact, the case. But first, a little digression on derived equivalences for people who haven't thought about them before. So, question is, when you have two algebraic varieties, let's say they're smooth, proper schemes over a field of a characteristic 0, when are their derived categories equivalent? So, of course, if the varieties are isomorphic, the derived categories are equivalent, but that's not very interesting. So, the first interesting example turns out to be what's called Mukai duality. So let me remind you what that is. So this is a famous paper of Mukai in the Nagoya journal in 1981. Suppose you have an abelian variety and x hat is its dual. So in dimension 1, an abelian variety is an elliptic curve, and the dual variety is canonically isomorphic to the original variety. But in higher dimensions, the dual and the curve are the dual and the original abelian variety could be distinct. So then you have this thing called the Poincare sheaf on x cross x hat. And that you get a derived equivalence from x to x hat. So the categories of coherent sheaves on these derived categories of coherent sheaves. It's not true if you don't take the derived category. The derived categories of coherent sheaves are equivalent for these two things, and this is the equivalence. You take a sheaf or a complex of sheaves, you pull it back to the product, you take the tensor product in the derived sense with the Poincare sheaf, and then you push it forward, again in the derived sense, down to the other variable. So you pull up, tensor, and push down. Okay, so that's called Mukai duality, and it's supposed to remind you of the Fourier transform. What's the situation with a Fourier transform? Well, then X is a real vector space, X hat is its dual, and the Poincare sheaf is replaced by the, the pairing e to the I x hat. Okay, this is the sort of canonical, pairing between the real vector space and its dual. And so the way you get the Fourier transform is you take a function of one variable, you pull it back to the product, multiply by this kernel and integrate. And then integration over what you're doing is integration over the fiber, which is really the same thing as derived push forward. And that gets you down to a function on the other variable. Okay, so even though it doesn't look like it, Mukai was really motivated by the Fourier transform. That's why this is often called Fourier-Mukai duality. Okay, so it's a kind of purely algebraic version of the Fourier transform. And then Orloff later proved that essentially all interesting examples of derived equivalences between different varieties, of course, they're sort of self-equivalences of D of x that come from either an automorphism of x or just shifting the degree, but those are not very interesting. All the interesting derived equivalences are of this type. And then there's also a theorem, which I didn't list here, of Orloff and Bondal that basically says that if you want to have if you want a derived equivalence between D of x and D of y, where x and y are not isomorphic to each other, then pretty much x and y have to be Calabi-Yau. I'm oversimplifying a little bit, but that's basically the context. So the fact that we're dealing with abelian varieties is not an accident, because these are sort of the simplest examples of Calabi-Yau manifolds. Okay, so of course, this applies to elliptic curves since they're self-dual. And then once you know how to do Mukai duality on an elliptic curve, maybe you can do fiber-wise Mukai duality on an elliptic fibration. So an elliptic fibration would be a situation where you have a higher dimensional manifold or variety and a map to a smaller dimensional thing, which you think of as a fibration. Doesn't have to be strictly a fibration. Let's say a, proper flat map or something like that. Maybe not even that. And then you try to do Mukai duality fiber-wise on the fibers, and then maybe you could get a derived equivalence between the total space of this elliptic fibration and the total space of a dual fibration, where you've dualized all the fibers. So Calderaro, in his thesis, discovered something very interesting about that. So he considered the situation where you have an elliptic fibration, but where there's no section. So the fibration is non-trivial. Okay, there's no section to the fibration. So then the dual fibration in this case is, the role of the dual fibration is played by what's called the relative Jacobian. I mean, roughly speaking, here the fibers are one-dimensional, so they're elliptic curves. So you're taking the Jacobian of each fiber-wise, and that gives you the relative Jacobian. So strictly speaking, that's the relative moduli space of semi-stable sheaves of rank 1 and degree 0 on the fibers. That gives you another elliptic fibration, and it has a canonical section because, of course, there's the trivial sheaf on each point, so each fiber. So you have a canonical section. So when you take this thing without a section and dualize it, you get something with a section. And so you could try to play this game of doing the Fourier-Mukai transform, but the problem is that usually there's no universal sheaf to play the role of the Poincare bundle, so then you're sort of out of luck. Because remember the recipe, you pull up tensor with a Poincare sheaf and then push down. So if there's no Poincare sheaf, you can't do that. So Calderaro discovered that there are two reasons why you may not have this Poincare sheaf. So one is that the J might have singularities, and that's easy to fix. You take a small resolution and you can sort of fix things up that way. Okay, so that's not such a serious problem. That's why I said semi-stable sheaves here. Really, you have to take the semi-stable sheaves and then compactify it, and stuff. But this is a less serious problem. The more serious problem is that the universal sheaf may only exist locally, but not globally. So it exists locally for the étale topology, but not globally. So, so what happens is that you get this L, the universal line bundle, and it exists locally, but if you want to think of it from a global point of view, it becomes what's called a twisted sheaf. So that means if you have three open sets for the étale topology on J, and the L is sort of defined locally on each of these, so you have the transition function on the overlap from U to V, and then the transition function from V to W, and then the transition function from W to U. And when you go around that triple, these transition functions may only agree up to a 2 cocycle. So that gives you a class, turns out gives you a class in étale 2 cohomology of J with coefficients in the multiplicative group. Okay, so this thing over here you recognize as being the cohomological Brauer group of J. And so what you get is a twisted sheaf, but it's twisted by this class in the Brauer group. And then the proof of Mukai duality still goes through, but then you have to replace sheaves by twisted sheaves. And so what you find out is that the derived category of X is equivalent to the derived category of J twisted by this alpha inverse, where alpha was this class over here. So the Mukai duality again goes by the usual recipe. You pull up to the product tensor and push down. So going from X to J, you pull up from X to X cross J. You want a tensor with L, which is an alpha twisted sheaf. So therefore, well, that's not quite the right thing, because you want, so you use L inverse instead. So that's an alpha inverse twisted sheaf. And then in the other direction, you start from J with something that's alpha inverse twisted. You pull it up, tensor with L, and then the two twists cancel out, the alpha and the alpha inverse, and you get something that's untwisted on the product, and then you can push it back down to X. So that's how you get this equivalence. So this is the main theorem of Calderaro's thesis. And in some sense, his idea and this kind of meta theorem are actually more interesting than the specific theorem that he writes down that he eventually published. So to see the meta theorem version of it, you should look in the thesis rather than the published version. But Anyway, so this is the idea. So now what we're going to do is to take this idea of twisted derived equivalence in a situation where you have an elliptic fibration without a section, and we're going to use this same idea over non-algebraically closed fields. So Calderaro only looked at cases over C, but now we're going to look at general fields and see what happens. So first, let's look at this case of the elliptic curve Orientifold theories. So suppose we have a complex elliptic curve E. The bar here is to remind you that it's over the algebraic closure. So over the algebraically closed field C, and as a free anti-holomorphic involution iota. So that was the case where there were no fixed points for the involution. So think of the iota as being the action of the Galois group on a curve C, which is really defined over R, but we're base changing to C. Okay. So you take the curve over R, base change to C, and look at the Galois group action. And the Galois group has no fixed points. So this, you can think of that the following way. You can think of C as a scheme over R. So you have a map to spec R, which is an elliptic fibration without a section. There's no section because if there were a section, that would mean that C would have to have a real point, which it doesn't. Okay. So in that situation, this is kind of scheme theoretically, it's an elliptic fibration without a section. So you can play Calderaro's game and take the Jacobian of C, E. So that when you base change to C, that'll be the same as this E bar. But the E will be a split elliptic curve in the sense that its set of real points has two circles in it. Okay, so we have two curves, C and E, which have the same complexification basically, but the Galois action is different in the two cases. So one of them corresponds to an elliptic fibration without a section, the other corresponds to an elliptic fibration with a section. So here's a theorem which I proved in the sort of special issue of JPAA for Chuck Weibel's birthday, and Dirk Kussen gave an independent proof in it by a different method in Journal of Noncommutative Geometry. So there's a Mukai duality equivalence between the derived category of C. Now we're working as schemes over R, so not over C, but over R. So derived category of C, which is this curve with no real points, and the derived category of E with a twist. And this alpha is a two torsion element in the Brauer group of E. If you take the Brauer group of E and divide out by the Brauer group of R, which is kind of uninteresting here, because that, the Brauer group of R is generated by the quaternions, and, so twisting by the quaternions would just amount to tensoring everything with the quaternions. So that doesn't really do anything very interesting. So forget about the Brauer group of R, and just look at the quotient. And this thing turns out to be a cyclic group of order 2, so it has a unique class in it. And that's the twisting class, and then you get this derived equivalence. And corresponding to that, of course, there's an equivalence of derived you have the equivalence of derived categories, you have equivalence of the algebraic K groups, you have the equivalence of the KR groups. All of that follows from this. So what I would claim is that this is a sort of algebraic geometry version of the T-duality of Orientifold string theories. And the twist alpha sort of roughly corresponds to the B field in the physics. Actually, more exactly, probably corresponds to the O-plane charge in the Orientifold. But what's funny about this is that in the Orientifold theory, when you think of it as a string theory, it's actually of type 2a. But here, we're sort of thinking of it as an algebraic variety over R and looking at the derived category of coherent sheaves. So we're sort of thinking of it from the 2b picture. So that's why in the 2a picture, it would be the O-plane charge. In the 2b picture, it's sort of the B field charge. Okay, so this is a kind of strange way to go from physics to algebraic geometry. Usually the route is a little more direct, but here this is, I explained all of this to try to tell you how I got interested in this particular topic, because on the face of it, it doesn't seem to have anything to do with mathematical physics, but that's the connection. Yeah. Right. 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 So that should correspond to some kind of twisted Mukai category. And what that is, I don't really know, because I don't even understand the non-twisted Mukai category. So, I mean, I'm not a symplectic geometer, so I don't understand Mukai categories. So I'm trying to stay clear of those. And that's why I'm just sort of working purely in the algebraic world. Okay. Yeah. Well, so as I said, we started, with a complex elliptic curve with an involution, anti-holomorphic involution. And then I'm trying to sort of rethink that as being a genus 1 curve, which is not necessarily an elliptic curve because it may not have a real point over R, and then asking what algebraic theorem would correspond to that T-duality of string theories, and it turns out to be this. So well, yeah, you could do it that way. I mean, that's probably equivalent point of view, but right, yeah. Well, this will sort of be convenient for what we're going to do next. So, all right. So far, this is all old stuff. So now in the last 20 minutes, let me get to some new things. So I want to talk about two generalizations of this. So they're joint work with two different groups of people. So the first case has to do with K3s. So suppose you have two elliptic curves over C, each which has a real J invariant, and then they admit anti-holomorphic involutions. And suppose, let's say, one of them is free and the other has a fixed set with two connected components. So that's what's called a split elliptic curve over R. Okay, so as we said, E1 with the free involution corresponds to a genus 1 curve with no real points over R, and E2 corresponds to a split elliptic curve over R. So you could take the duality that I just talked about and just cross it with E2. Of course, that doesn't do very much, but now you can do something a little more. You can divide out by multiplication by -1. That gives you a singular surface, and then resolve the 16 singularities, and then you get a Kummer K3. Okay, so this Kummer K3 by projection onto E2 divided out by plus or minus 1, which is P1, gives you an isotrivial elliptic fibration, which is defined over R, but it doesn't have a section over R. So you could play the same game. And when you take the relative Jacobian, you get a dual elliptically fibered K3, which is also defined over R, but this time it has a section. And so again, you get a derived equivalence like this between, so this is over R now. One is a K3 with no real points, and the other is a K3 with a twist in the Brauer group. And you can interpret this in terms of duality of Orientifold type 2b string theories on K3s. So that this sort of grew out of a joint project with Chuck Duran, Andreas Malmedier, and Stefan Mendes-Diaz. Chuck and Andreas were supposed to be here this week, but at least you'll hear Andreas virtually on Friday. Okay. All right, so that's generalization number one. So now let me look at a second generalization. So this is joint work with my Maryland colleague, Niranjan Ramachandran. And it's mostly written up, but paper hasn't been posted yet. So suppose K is a field of characteristic 0 for simplicity, and C is a smooth, connected projective curve of genus 1 over K. And E is its Jacobian, so that's an elliptic curve over K. So that's like the case we were looking at before, in the case where K was equal to R. Then C, it turns out, is a torsor over E. So it defines a class delta of C, which lives in the étale 1 cohomology of spec K with values in this group of K bar points of E, with its Galois action. Okay, so we have a smooth curve of genus 1. It's a torsor for an elliptic curve. These things come up a lot in number theory. And so now look at the canonical map from E to spec K. So this is defined over K, and it's split by the section that goes back that sends, the unique closed point here to the base point in the elliptic curve. So in the Leray spectral sequence for this map here, all the differentials that land in the bottom row have to vanish because of the splitting. So there's no differential D2 from E11 to E30. And also E02, which would be that would basically be H2 étale of the elliptic curve, that vanishes by Tsen's theorem. So therefore, the Brauer group of E just splits up as the relative Brauer group plus the Brauer group of K. So this is now you have a canonical splitting because you have the splitting given by this section. And this is the relative Brauer group. Okay, and so in this situation, you can write down what that relative Brauer group is. So this has been known for a long time. You can find it, for example, in several papers of Skora-Bogotov and various other people. So this étale cohomology group, which classifies the torsors, is canonically isomorphic to the relative Brauer group. Okay, so this immediately follows from the Leray spectral sequence, plus the fact that the spectral sequence has a section plus Tsen's theorem that gives you the vanishing of E202. Okay, so that's fairly elementary. So here's our theorem. So let's C be our genus 1 curve. and let beta be its class as a torsor. So then you get a Mukai duality equivalence between the derived category of C and the derived category of the Jacobian twisted by beta inverse. So that's just like the theorem that we wrote down in the case where K was equal to R. So this holds over general fields. I mean, you can do some things over in characteristic P also, but there's some additional complications that I don't want to get into. So just doing this here for simplicity in characteristic 0. Okay, so that's the theorem. And since we have a few minutes, maybe I'll just tell you how this is proved. Let me scroll up here. Oops. So this doesn't take up the whole screen there. No, I guess I can't do that. All right. Anyway, so that's the theorem. So now, yeah, I was told when we use the projector and the blackboard simultaneously, you can only use the center board. All right. So, all right. So how would you prove this? So, the idea is the following. So, we want to play the Calderora's game on C crossover spec K with E, and we want the universal sheaf over here to live on this thing, but because your elliptic fibration doesn't have a section, there won't be any such sheaf unless you think of it as a twisted sheaf. So what's the correct framework for understanding this? Well, there's a nice paper of Max Lieblich that sort of explains kind of general philosophy for dealing with things like this. So what you should do is, instead of looking at E, which is the Jacobian, you look over E at the let's say 0 component of the, so this is the 0 component of the Picard stack. Okay, so maybe I'm not necessarily getting back to your question about why aren't we using stacks. So actually they are needed here at this point. Okay, so you look at the Picard stack. So the Picard stack sort of projects down to E, but this thing over here is the GM gerb. So this gerb is given by a twisting, and that twisting, so it has a so this thing is the Brauer group, of course. So that's the twisting that we're interested in for defining this L. And we just have to show that this basically coincides with the class of the torsor C viewed as a torsor for E. Okay, so how do you do this? Well, if you take this gerb and you sort of push it down to spec K, then it turns out that gives you a torsor, which is exactly this twisting class. And so if you can show, sorry, that gives you so push down. Here's a class in H1, a tall of spec K coefficients in, say, R1. Something like that. And we just have to show that this coincides basically with that delta that we had before. Okay, so what you do is you just you write down this torsor that you get over here, and you can just see directly that that torsor coincides with the torsor that you started with. So therefore, you get a universal sheaf on C cross E, which is alpha twisted, where alpha is this, or beta twisted, where beta is this thing over here. And then you just plug that into Caldera's machine, you know, and you apply his meta theorem, and that gives you the answer. So that's the method of proof. It's actually pretty straightforward when you think about it from this point of view. But so I'm not claiming that there's anything super deep here, but it, you know, it's kind of interesting to see how these twisted derived equivalences show up, and how they explain how to compute the derived category of a curve that doesn't have any rational points, and what that has to do with mathematical physics. I admit the connections may be a little tenuous, but you know, at least there was a there was a path through mathematics that started at one and arrived at the other, even if it's a little convoluted. Okay, so that's it. Thank you.
Thank you very much. What are the questions and comments? What about K-free surfaces?
Well, K3 surfaces in general are very interesting and very complicated. So you mean, what about, let's say, K3 surfaces over general fields, not over, let's say, algebraically closed fields of characteristic 0? So yeah, that's a really complicated subject. And so far, we have a total of one example, basically. But yeah, I think that's a good subject for research, and I think, you know, one ought to be able to do a lot there. I just, you know, we've just barely gotten started, but yeah.
Tyler?
So for cubic fourfolds, their derived categories can often have this kind of Kuznetsov component, where it's usually a twisted K3. But you can also write that as matrix factorizations for a certain Landau-Ginzburg model. Is there any hope for writing these kind of real twisted derived categories in a natural way using matrix factorizations, or?
That's a good question, but I know nothing about it.
Okay.
I mean, yeah. Sounds like an interesting thing to try, but I you know, I don't know anything about it at all. Yeah.
All right, thanks.
Yeah.
More questions, comments? Directions of inquiry? All right, then let's thank Jonathan again. And we'll resume in about 5 minutes or so, 7 minutes maybe. Very nice to see our physics teacher give us some intuition. Right, there was all of these things that came from physics in the 90s, right?
Well, this came from physics also, actually.
Yeah. But it's like right.
Fourier, you might say, was really a physicist, but yeah.
Awesome. Thank you very much.
Okay, thanks.
Very good, very good.